Hello friends, in this session we will see stability using state space. So far we know that the state space model is shown by x dot equal to ax plus bu and y equal to cx plus du. We have had a detailed conversation, right, about this one. Anyways, yes. So now the transfer function of the state space model. For the state space model, the transfer function that is given as t of s, which is equal to c into si minus a inverse into b plus d. Is it right? Yes, definitely. Now we know that inverse of a matrix is also known as adjoint of that particular matrix divided by the determinant of the matrix. Right. So if you just see here, let me just keep this thing, let me just keep this C and this B and everything same and let me just focus on this inverse. So if you see here, this inverse Si minus A inverse, if you see, this is nothing but what? Yes, adjoint of Si minus A upon determinant of Si minus A, right? Adjoint of Si minus A divided by determinant of Si minus A. Now if you just see here, this is the transfer function, right? Yes. What is the denominator of this transfer function? Definitely this is the denominator of the transfer function. Yes. Now we know that denominator of the transfer function gives you poles. Am I right or wrong? Denominator of the transfer function gives you poles, right? And here if you see, from this particular state space model, you had got some transfer function whose denominator is Si minus A, whose denominator is determinant of Si minus A, and so I am saying that this will give you the poles. Am I right? Yes. Now if you remember in the characteristic equation, when we were talking about characteristic equation, what do we do in our transfer function approach? If you remember, we had something called as characteristic equation. So there we used to have, some, let us say you have some closed loop transfer function g of s upon 1 plus g of s into h of s, right? So there this was the denominator, so you used to equate this to 0. So there 1 plus gh, which is there, equal to 0, this was your characteristic equation. But here 1 plus gh will not be the characteristic equation, rather now the characteristic equation will be this one, determinant of Si minus A. Why? Because this you have got from the state space model. So if you just think of the characteristic equation for now, it is going to become, we are going to have a new characteristic equation. Actually the concept remains same. Just think about it, that in our transfer function approach, right, in our transfer function approach we did so much things related to the stability. We used RH criteria, we used something called as polar plot, something called as Nyquist plot, and stuff like that, right? So that was all done in order to check if the system is stable or not. So yes, definitely the stability concept will be there in case of our modern control theory as well. So yes, this is nothing but the characteristic equation. So now the characteristic equation in our state space thing is going to be Si minus A, determinant of Si minus A equal to 0. The same thing this you had in transfer function approach. Now the same thing you have here. How we have here? Because this particular red, it used to be the denominator of the transfer function, whereas similarly now the denominator of the transfer function is nothing but Si minus A inverse. So this is the characteristic equation. Am I right? Now in our classical control systems, we used to call the roots of this equation, roots of the characteristic equation. If you think of, in our classical approach, we used to call them as poles, right? But from a perspective of linear algebra, or from the perspective of mathematics or matrices, or mathematics if we think of, or we can say by perspective of linear algebra to be specific, linear algebra if you see, then yes, definitely this roots of the characteristic equation are called as eigenvalues. Eigenvalues, right? Because you have already studied this in your mathematics. Now if you just think of the same, the determinant of Si minus A is called as poles, and the same is also called as eigenvalues, which means poles of the transfer function is nothing but eigenvalues of matrix A. So now you have understood another approach, that yes, for a transfer function, the poles of the transfer function are nothing but eigenvalues of A. Eigenvalues of A. Right. So now let us try to understand what is the condition for stability. Yes. So now what is the condition for stability? Because that is what is important. We have seen that in our classical approach, we have seen that the poles which are there, poles of the system, that should be on the left half of open S plane. Am I right? Then only we used to call that the system is stable in our classical approach. But now in our state space approach, rather than poles, I will be using the terms as eigenvalues. They are basically same only, no, poles or eigenvalues, both are same. Why? Because characteristic equation, right? Anyways, so eigenvalues. Now eigenvalues, if the eigenvalues lie on the left half, this is left half, or we can say open left half of S plane, then we say that it is going to be stable system. This is the condition for stability in our state space, that yes, eigenvalue should lie on the left half of S plane, or we can say that the poles have to be there on left half of S plane. So whatever things we have already learned, those same things are applied here, right? Yes. Now let us try to apply this stability thing to some practical systems, to some practical matrices. Let us see. If I try to apply this to a, let us say, diagonal canonical form, if I try to apply this to, let us say, diagonal canonical form, then let us say what happens. Now we know that the diagonal canonical form, this A which is there, because since it is diagonal canonical form, then definitely there will be non-repeated poles, because if poles are repeated, then they are shown in case of a Jordan canonical form, we have already seen. So if you see here in this A, I may have some poles like, minus p1, minus p2, and so on up to, let us say, minus pn, and everywhere I'm going to have this 0, this 0, and this 0, 0, and 0, right? This is what is diagonal form, this is the A. Now if you know from the basics of the linear algebra basics, if you know what are the eigenvalues of diagonal matrix, what are the eigenvalues of the diagonal matrix, from the linear algebra you have seen that it is nothing but diagonal elements itself. Just see how beautifully we are linking everything here. We have studied about stability in our transfer function approach, the same stability we have now. We have studied about matrices in case of our linear algebra, that also, right? And we have just seen, the importance of diagonal canonical form, what is that? That yes, since this matrix A, which is also called as the system matrix, why? Because it tells you about the stability. How it tells you about the stability is that because the diagonal elements are nothing but the poles, or I can say the eigenvalues of the matrix A. So here if you see what are the eigenvalues of matrix A, then they are going to be, yes, minus p1, minus p2, up to minus Pn and so on. So these are the eigenvalues of matrix A. Now let us take examples to the practical system. Let us think of. Let me take the first matrix A equal to minus 3 0 0 minus 2. You have to comment on the stability, whether it is a stable system or an unstable system. Now if you see here, is it in a diagonal canonical form? Yes, definitely. Let me use another pen. Yes, it is definitely in a diagonal canonical form, right? So what are eigenvalues of A? What are eigenvalues of A? We have already seen that it is nothing but the, what do you say, diagonal elements. So here diagonal elements are minus 3 and minus 2. So yes, definitely eigenvalues are going to be minus 3 comma minus 2, right? Now if you see here, are they lying on the left half of S plane? Yes, if you just plot this one, so this will be somewhere around minus 2, this will be around minus 3. So it is in the left half of the S plane. That is the reason this is a stable system. This is a stable system. Now let us think of second example. Let me take second example. A equal to, let us think of, minus 3 1 0 0 minus 3 0, and let me have 0 0 2. You please tell me which form it is. It is Jordan's canonical form. Just see how easily we can think of the stability, how easily we can say, because student may say that, sir, we are understanding the things about CCF, OCF, DCF, JCF and all. Yes, the importance is this one, that just by observation, just by clear cut observation, you will be able to comment on the stability. That's the beauty of these forms. Anyways, so this is a JCF, right? Now what are the eigenvalues for this matrix? What are these eigenvalues of matrix A? Yes, definitely it is also going to be what, minus 3 and 2. So eigenvalues are minus 3 and 2. So if you try to plot them on the polar plot, then you get this as minus 3 and minus 3, you have 2 poles. So this is minus 3, you have got 2 poles over here, and yes, you have 1 pole over here, which is 2. So from this we infer that because of this 2, because of this one eigenvalue which is lying on the right half of the S plane, or we can say because of this one pole which is on the right half, we can say that the system is unstable. Getting my point? System is unstable. Now let us take another example. Let us see. Yes. So now it is in what form? It is in definitely controllable canonical form, because you have this 0 1 0, you have 0 0 1, and then you have this last one, minus 1 minus 3 minus 3. Right. Now what are we supposed to know? Because see, controllable canonical form does not give you stability directly, right? So let us try to form the transfer function. So yes, in order to form the transfer function, you may need this, right? Si minus A inverse, matrix Si minus A inverse, right? But do you actually need this? No. Why? Because we know that this last row which is there, this last row of this matrix A is formed from the denominator, of the transfer function, right? So which means that this last row will give me the denominator of the transfer function. And what is the denominator of the transfer function here? Yes, it is nothing but the characteristic equation. So just if I have this characteristic equation, I will be able to comment on the stability of the system, right? So now let us see. Yes, so now if you see, yes, we have to go in the reverse order, right? Or we can just say that, yes, for this one, what will be the transfer function here? Yes, transfer function is going to be, it is going to be s cube plus 3s squared plus 3s plus 1. How do you know that? You just go in the reverse way, and write it here with a negative sign, which means this 1 will now here become minus 1, this 3 goes here and becomes minus 3, and this 3 goes here and becomes minus 3. That is the conclusion. So this is not a transfer function, by the way. This is the characteristic equation. This is the characteristic equation. So what do you get here? You get that the characteristic equation is nothing but s cube plus 3s squared plus 3s plus 1. Is that all right? Yes. Now see here, what are the roots of this characteristic equation? Because if I equate this to 0, it becomes characteristic equation. So what are the roots now? What are the roots now? These roots will be nothing but the poles. Roots are nothing but the poles. What are the poles? If you just place this in your scientific calculator, you will get the answer to be s equal to -1 comma -1 comma -1. So these are the three poles, which means all the three lie on the -1, -1 and -1. All the three poles lie here. Where are they lying? They are lying in the left half of the s plane, which means system is stable. System is stable. Now, yes, let me think of another question. Question number 4. Let us say that a is equal to, so if you see here, this is going to be 0 1 0, this is going to be 0 0 1, and this is -2 -5 -6. So this is nothing but observable canonical form. If you see, yes, it is observable canonical form, right? So again we are going to go in a reverse order here, this way only, right? So if you just think of here, let me try to find the characteristic equation. What will be the characteristic equation there? What will be the characteristic equation here? It is just going to be s cube plus 6s squared plus 5s plus 2, which is equal to 0. See, what you have to do, you just go in this reverse order as usual we did here. So the same way we come here, that's it. Or if you don't understand this, try to form this into a controllable canonical form. If I try to form in controllable canonical form, what will be a is going to be, yes, 0 1 0 0 0 1, this is for sure. And because we are going in this reverse direction, what do I get here is this +2 will become -2 because we have to change the sign as well. This +5 is going to become -5, and this +6 is going to become -6, right? Now if I try to find OCF, what is OCF? OCF will be transpose of this matrix, so it will be A transpose, right? So if I try to find this OCF, it is going to become transpose of this. So this first row will become first column of this, so it becomes 0 1 0. Similarly, the second row will become second column of this, which means it becomes 0 0 1, and this third row will become third column of it, and it becomes -2 -5 -6. I hope you are understanding this point. So this is the OCF, and then yes, definitely for this OCF what we have is this one, right? Now, so the characteristic equation that you have is nothing but what? S cube plus 6s squared plus 5s plus 2 equal to 0. If you just place this in your calculator, the answer that you get is, the poles that you get is s equal to -5.09, -0.45, plus minus, this is the complex pole, which is j 0.43. So if you see all of these poles, if you see, one is here at -5.09 and other ones are here, two poles, right? Which means all are on the left half of the s plane, which means system is stable. System is stable. Now let us think of another question. Yes, now you please tell me, is it in CCF? No, it is not in CCF. Why? Because in CCF you need 0 1 0, 0 0 1, and so on. Is it OCF? No. Is it not CCF? So no point of having OCF. Is it diagonal canonical form? No. Why? Because other elements are also present. Is it Jordan canonical form? No. Which means all our four standard forms have been failed. All our four standard forms have been failed. So now here you will understand what was the advantage of having the system in the four standard canonical forms. The advantage was that we were able to check the stability very easily. Even if it is CCF, even it is OCF, we were able to find the characteristic equation in a very easy way. Whereas in case of diagonal canonical form, or in case of a Jordan canonical form, just by observing A, we could say that yes, it is a stable system or a unstable system. But now since the given matrix A, it is not in any of the standard canonical forms, we have no other option than solving the determinant. In the sense, we know that characteristic equation is Si minus A. So for this one, we have to find determinant of Si minus A. There is no other option. Whereas if you see all the previous cases, even in this case, even in this case, even in this case, right, even in this case, we have not at all calculated the characteristic equation from Si minus A thing, right? We have not at all used determinant of Si minus A, but now we are supposed to use determinant of Si minus A. Why? Because it is not in any standard form. So that was the advantage of having a standard form. I hope you are understanding this concept, right? Now see here. Yes, so now when I think of Si minus A, determinant of Si minus A, what does that mean? Si minus A in the sense S into I, right? So it becomes S0 0S. Already we know that, right? Now what is A minus A, right? So what is A here? A is going to be minus 3 5 2, right? If I make them, what do I get here? What do I get here? I get this matrix as this one. What is the matrix? Si minus A matrix. What is, let me take the matrix first. Si minus A matrix. What is the matrix? Yes, this S minus 1 is going to be S minus 1, right? Then this 0 minus 3 is going to be minus 3. Then this 0 minus 5 is going to be minus 5. And yes, this S minus 2 is going to be S minus 2. It is very simple, right? Now yes, remember the shortcuts wherever it is easy and you can understand them in a simple way, right? Don't try to be under that impression that no sir, we want shortcut, we want shortcut. No, no, no. Shortcuts are important, but at particular places only, not everywhere. Anyways, now let us try to find the determinant of Si minus A. So if I get determinant of Si minus A, which means I need to apply the determinant here. If I apply the determinants here, what do I get? This into this, S minus 1 into S minus 2, minus this into this. So it becomes minus 3 into minus 5. So what do I get here? I get here S into S is S squared minus S into minus 2 minus S into 2 is 2S again minus S then plus 2, right? And this is going to be plus 15 and this minus sign taken here, so it becomes minus 15. So if I think of the characteristic equation in totality, if you see, it becomes S squared minus 2S minus 2S minus S becomes minus 3S, right? Combined it becomes minus 3S, and plus 2 minus 15 becomes minus 13. It is equal to 0. This is the characteristic equation, right? Now if you just place this in your calculator, you get S equal to 5.4, you get S equal to minus 2.4. So if you see here this minus 2.4, right, since S equal to minus 2.4, what about this one? Yes, if you think of this S equal to 5.4, this is stable. What about S equal to 5.4? S equal to 5.4 in the sense the pole is here, which means it is unstable, This is the thing we have understood. Now you could have applied another thing also. We have known something called as Rao-Hurwitz criterion. Why we just don't need that? We just think about Hurwitz equation. What is Hurwitz equation? Hurwitz equation says that the characteristic equation which is there, all the signs have to be same. All signs have to be same. Are they same? Here you have plus, here you have minus, here you have minus. So all signs are not same, which means it is not a Hurwitz equation. Not a Hurwitz equation, which means the system is unstable. Directly you can tell that, right? So in such a way, you just have to interconnect or interlink all the things together, and then you can easily solve the problems. Thank you.